Swayam Prabha. Digital India. Educated India.
Hello and welcome. Let us now start with our introductory lecture on B-spline segments or curves. This is lecture number 19. Here we'll talk about polynomial splines in general. But first, why B-splines? Rather, why an alternative approach or method to design curves? Let's look at some composite curve models that we had discussed previously. First, composite Ferguson curves. For C1 composite Ferguson curve, the model is naturally continuous at junction points. However, to specify the first order or slope information is not very intuitive from the designer's perspective. And this is true especially in three-dimensional case. To specify individual components, the x, y, and z components of slope is not very straightforward for a designer. For C2 composite Ferguson curves, the slope information is required at only two endpoints. All the intermediate slopes will get computed due to C2 continuity conditions. However, there is no local shape control for the entire curve. In fact, C1 composite Ferguson curves can be locally controlled in shape. In case of composite Bezier curves that we had recently studied, once again, individual segments constituting a composite Bezier curve do not have local control. Position of data points of these subsequent segments are constrained. Anyhow, this is what I emphasize, and this is what is going to motivate us to pursue design of spline segments and curves. No local control in the Ferguson and composite Bezier curves, particularly C2 composite Bezier curves and Ferguson curves that we had studied before. We would, as designers, like to achieve local control in shape design of curves. The following few lectures will be devoted entirely to this discussion. After motivating us enough to study splines, first let us figure what splines are. How do you think Britishers, Portuguese, and Spaniards could build huge ships about 300 to 400, maybe 500 years ago and travel across the world? They used something called ducts, and within or in between those ducts, they used to place wooden strip or metallic strips and get the shape of the hull of the ship. These strips used to remain within these ducts for days and days. They then possibly did not know that what they are designing are essentially spline curves protruded in the third dimension. If you look at these individual segments, each segment is a simply supported beam. You might want to revisit the discussions in your second year solid mechanics course or strength of materials course. Each beam, therefore, will appear like this. simply supported at both ends. Let's try to analyze the structure using Euler-Bernoulli beam theory that assumes small deformation. This expression or relation would be very familiar to mechanical engineers or burgeoning mechanical engineers. It says EI times chi is equal to EI times the second derivative of the vertical deflection with respect to x squared, where x is along the beam length, which is equal to a times x plus b. EI is the flexural rigidity. Chi is the curvature, and for small deformation, the curvature is given by d2y over dx squared. Y is the vertical deflection. A and B are known constants. 10 points for guessing what this is. You're right. This is the moment at any cross section. If we integrate this relation twice, we'll have y equals a times x cubed over 6ei plus b times x squared over 2ei plus c1x plus c2. c1 and c2 are unknown constants which you can compute using boundary conditions. Boundary conditions at say x equals 0 and x equals L, the beam length, are that the vertical deflections are 0. Why? Because we are considering a simply supported beam. If we put x equals 0 here, and if you know that y equals 0, this would mean C2 equals 0. And for x equals L, we can substitute y equals 0, x equals L, and find what C1 is. So C1 will be minus of AL squared over 6EI minus BL over 2EI. If we substitute the values of C1 and C2 back into this equation, we have y equals minus a times L squared x minus x cubed over 6EI minus b times Lx minus x squared over 2EI. Once again, L is the beam length. What do we see? We see the vertical deflection over here as a function of the coordinate along the beam length. And we can also observe what the relation or what the nature of the relation is. It is cubic for values of x between 0 and L across the entire simply supported beam segment. One should note that Ax plus b, which would represent the moment conditions at any cross section, is matched at endpoints due to equilibrium. If we look or if we observe this relation closely, this seems to be inherently a C2 continuous curve, because you would be able to differentiate this at least twice. If we go back and if we try to differentiate this thing the third time, d3y over dx cubed will be equal to a, and this value a will be different across different contiguous simply supported segments. What do we note now? We can comment on what we are going to term as a cubic spline. A cubic spline is a curve for which the second derivative is continuous throughout the interval of definition. Let's go back to this figure here. We are considering this entire strip, and what we are saying is this strip is a cubic spline. It may be possible for us to generalize and define what an n minus 1th degree or an nth degree spline is. So the definition of a spline: an nth order which is an n-1th degree curve. A spline is a curve which is C n-2 continuous in the entire domain of definition. This means that the n-2th derivative of the curve exists anywhere in the above domain. A little note about what order is and what degree is. Order is always degree plus 1. For example, an nth order curve will be of degree n-1. The basic question, why splines? Recall our discussion on Bernstein polynomials when we are discussing Bezier segments and composite Bezier curves. We would like to develop basis functions which are very similar to Bernstein polynomials. Let us call those functions as psi sub I as a function of parameter t. T here may or may not be restricted to values between 0 and 1. Also recall the salient properties of Bernstein polynomials. Remember that they are barycentric in nature, that all these Bernstein polynomials are positive or non-negative in the respective parameter intervals, that is 0 and 1, and that all these polynomials, they sum to 1, no matter what the t value or what the parameter value is. We would want these barycentric properties to be local now. What do I mean here? Bernstein polynomials, they sum to 1 for values of t in between 0 and 1. Here we would want not all but some spline basis functions, psi's, to sum to 1 in some sub-interval of t. And of course, we would want these basis functions, psi I, to be bell-shaped. Say, for example, if you are trying to plot different spline basis functions, psi i's, one of those psi i's will look like this. Let's say for parameter values between t0 and t3. The second one will maybe look like this, say in between t1 and t4. The third one may look like this, between, let's say, t2 and t5. And we can keep on going until the final one may look like this. Coming back to this statement, local barycentricity, we do not want all these psi's to sum to 1. Rather, we would want now only a few of these basis functions to sum to 1, irrespective of how the rest of the functions behave. And it is this that would give us the local control property. We'll see later how. Let's continue our discussion on polynomial splines. Let's consider one of these functions here, and let's try to design that function. Let's say, for example, that this function is a cubic polynomial, number 1. Number 2, that it is designed in a similar way as a piecewise continuous curve that we had seen when discussing Ferguson composite curves and Bezier composite curves. Let me explain this on the board. I first draw the parameter axis t. I draw the vertical axis that would represent the value of psi I. So remember, I am now constructing a bell-shaped basis function, or a bell-shaped piecewise composite curve. This is how I would do this. I'll start with some parameter value, let's say T0, and I'll end at some other parameter value, say Tf. And in between, I'll construct different polynomial segments. Let's say in between T0 and T1, I construct this segment. In between T1 and say T2, I construct another segment. And in between T2 and Tf, I construct the third segment. Segment 1, segment 2, segment 3. Each of these segments will be pure polynomials. As you would notice, there would be junction points. In this case, we'll have two junction points here. And like we had discussed in case of Ferguson-Bezier curves, we will have to impose continuity conditions. C0, C1, up till Cn minus 2. In case this bell-shaped curve is an nth order spline. Let's now continue with some mathematics. Let me work with a few of these polynomial segments. This is the parameter axis. This is the axis that will correspond to non-zero values of the basis functions. And let's say this is a generic spline curve. We have these points at parameter value t I minus 1. We have the value of this generic spline curve as y minus 1. At ti, we have the value yi. Likewise, at ti plus 1, we have the value yi plus 1, and so on and so forth. Let's say these ordered pairs are given to us, and we have to construct a generic spline. Let's say that we are going to be constructing phi t, which would be a cubic spline in each sub-interval ti minus 1 to ti. What would this mean? At these junction points, we would want that the spline is slope continuous, and also we would want that the second derivative of the entire spline is continuous. Of course, position continuity is implicit. Some terminology. These parameter values ti minus 1, ti, ti plus 1, and so on and so forth, they are fixed values for a given spline. For I equals 0, 1 up till n, and these fixed values for t are called knots. You might want to keep this in mind because we are going to be frequently using the term knots later on. Going further, these spans ti minus 1 to ti, ti to ti plus 1 for different values of I are called knot spans. If the knots are equally spaced, That would mean that if these knot intervals are of constant length, the knot sequence is said to be uniform. Otherwise, if these fixed parameter values are arbitrarily placed, the knot span is called non-uniform. We assume here that these knots are arranged in ascending order. That means Ti minus 1 is smaller than Ti, and so on and so forth. Let's enlarge this figure now. Same, we have the knots now, and we have the values of this composite spline at each knot. Let phi sub I be a spline in the ith span. The ith span would be corresponding to the values of t in between Ti and Ti plus 1. So here, this is the ith span. Let's assume that in the first span, for values of t in between t0 and t1, phi 0 t0 and phi 0 t1 are known. Coming back to the board, this is my parameter axis t. I start with parameter values t0, t1, t2, and so on and so forth. Of course, I am interested in constructing a bell-shaped basis function, but let me generalize this discussion here. This is my phi axis. Let me start constructing a spline curve from here. At t0, let me assume that I know the value of phi 0. Likewise, at t1, let me assume that I know the value of phi 0 again. Phi 0 would be the curve in between t0 and t1. That is within the first knot span. Since I am trying to construct a cubic curve or a cubic polynomial, let's say let it have a shape like this. I have these two conditions. I would need two more conditions. What are they? They can be the slope and the second derivative at the first parameter value. Let's assume that we have the slope information given here and also the information corresponding to the second derivative given here. Three conditions. The fourth condition, this is a cubic polynomial. I would be able to determine this polynomial. This is the first piece of the cubic spline that we are interested in constructing. How about the second one? We would need four conditions again, because this again would be a pure cubic polynomial. Let's construct those conditions. Let me call this phi 1 t. Phi 1 t at t2, let's say, is known. That is the first condition. How about the other three conditions? let's concentrate on this point here, which is the junction point. Do I know the value of phi 1 at t equals t1? Yes, and that is the same as phi 0 at t1, which comes from here. This would give us position continuity or C0 continuity. Let's recall now what would be a cubic spline. A cubic spline would be such that this entire curve would be C2 continuous throughout. That would mean that the second derivative should be uniquely available at any point on this curve. In a sense, we need to ensure that we have not only C1 continuity or the slope continuity, but also continuity in the second derivative at this junction point. What would that mean? This would mean that we would be able to generate two more conditions. The slope should be equal, and the second derivative would also be equal. The slope and the second derivative for this segment and the slope and the second derivative for this segment. This ensures slope continuity, and this condition ensures the continuity in the second derivative. In a sense, for this cubic segment phi 1t, we now have four conditions: the value at t equals t2, the value at not t1, the slope continuity condition, and the curvature continuity condition. Since this again is a cubic segment with four conditions, we should be able to determine the four unknowns, constructing the third segment. We would construct the third segment in an exact fashion that we used to construct the second segment. Let me call this segment phi 2. Let this not value be t3. Let me assume the value right here, phi 2, t3. Let me assume that this is known. At this junction point, we will have C0 continuity, C1 continuity, and C2 continuity. Now that you know what the second segment is, you can generate these three conditions. Three conditions here, the fourth condition here, the third segment of the spline is known. Once again, let me emphasize that this is a cubic spline. By definition, a cubic spline is supposed to have C2 continuity condition intact throughout. If we keep on constructing subsequent segments, we would be able to extend this curve as much as we want. In other words, to any knot value we want. By the way, any idea as to how we can make the shape of this spline very similar to a bell-shaped curve? Well, one way would be to start with the first value as 0 and end with the last value as 0. How about the slope and curvature? Let's reserve this discussion for later. So this is a summary of the construction procedure that I had just described on board. In a sense, cubic segments, phi it, I going from 0 to n minus 1, over the entire knot span can be determined. But should the spline be constructed this way? Possibly not. Because if there are errors to start with from here, they keep on getting accumulated. They keep on getting added. To avoid that, we have a slightly different way of constructing polynomial splines. Let's start with this figure again. Let's say we know the values at different knots of the spline. The values would be yi minus 1 at ti minus 1, yi at ti, and yi plus 1 at ti plus 1, and so on and so forth. Or let's discuss an alternate approach. Since each segment over here, represented by phi I, is cubic, I can write phi I in this form as a function of parameter t. Phi I is equal to a sub 0 plus a sub 1 times t plus a sub 2 times t squared plus a3 times t cubed. a0, a1, a2, and a3 are unknown constants or coefficients. And phi I would be defined within the knot span ti and ti plus 1, right here. Now let's say that Si and Si plus 1 are unknown slopes at values of t equals ti and t equals ti plus 1. Okay, now in terms of the two positions and two slopes, what do we have? We have a linear system in the coefficients. We'll have the coefficient matrix as 1 ti, ti squared, ti cubed, 1 ti plus 1, ti plus 1 the whole squared, ti plus 1 the whole cube, 0, 1, 2 ti, 3 ti squared, 0, 1, 2 ti plus 1, and 3 ti plus 1 squared. What would these coefficients correspond to? Well, this corresponds to the first equation if we substitute phi I equals yi for t equals ti. This row here corresponds to the second equation. Phi I at ti plus 1 is yi plus 1. If we differentiate this, we'll have a0, which is gone. We'll have a1 plus 2a2 plus 3a3 t squared. If we substitute t equals ti, these two terms are 0, corresponding to the first coefficient, a0. These two terms will be 1. We'll have a1 here. These two terms will be corresponding to ti and ti plus 1 times 2, first differentiation of this term. And these two terms here would be corresponding to the first differentiation of this term here for values of ti and ti plus 1. This is a column vector comprising unknown coefficients, and these are the respective y and y plus 1 values here, and also the values of the two slopes, si and si plus 1. We know this column, we know this coefficient matrix, or this 4 by 4 matrix. We can compute what A0, A1, A2, and A3 are, which would be this 4 by 4 matrix, inverse of that, times yi, yi plus 1, si, and si plus 1. But wait a minute. When did I tell you that si and si plus 1 are knowns? We just said let the slopes be unknowns at these 2 points. Let's see where this takes us. Okay, this is a little more involved expression here. Phi it can be represented in matrix form or in compact form. Okay, so the first matrix will be the 1 by 4 matrix in terms of parameter values t, 1, t, t squared, and t cubed. This is a very complex looking 4 by 4 matrix, and this is the geometric matrix pertaining to the geometric information here, the 2 points and the 2 slopes. What is this 4 by 4 matrix? The inverse of this matrix here. Okay, let me read out the terms. The first term, ti plus 1 minus 3ti times ti plus 1 squared over hi cubed. 3 times ti plus 1 minus ti times ti squared over hi cubed minus ti plus 1 squared over hi squared minus ti squared ti plus 1 over hi squared. Second row, 6 ti plus 1 over hi cubed minus 6 ti plus 1 over hi cubed, 2 times ti plus 1 times ti plus 1. The fourth term, ti plus 2 times ti plus 1 times ti over hi squared. In the third row, we have minus 3 ti plus ti plus 1 over hi cubed, 3 ti plus ti plus 1 over hi cubed minus ti plus 2 ti plus 1 over hi squared minus 2 ti plus ti plus 1 over hi squared. In the fourth row, we have 2 over hi cubed minus 2 over hi cubed, 1 over hi squared, and 1 over hi squared. Okay, what is hi? Hi is the difference ti plus 1 minus ti. Let's continue with this math. Okay, now the entire cubic spline is essentially a set of each cubic segment, phi it, I going from 0 to n minus 1. Okay, and this spline is position and slope continuous within the entire knot span, going from t0 up till tn. Notice that since phi I is a cubic spline, it needs to be having unique second derivatives at each value of t in the entire span. Okay, this would mean that phi I minus 1, which is the I minus 1th segment, the second derivative of that at the knot value ti should be equal to phi the ith polynomial segment, the second derivative of that at ti. From that previous complex relation, it should be possible for us to compute what the second derivative is. This coefficient matrix will not change. This geometric column vector will not change. What would change would be this first 1 by 4 row matrix. If I differentiate the previous relation twice, the first term is 0, the second term is 0, the third term is 2, and the fourth term is 6 times t. These two matrices are constants in differentiation. All I need to do is plug in this expression here in this equation for value t equals ti for both I minus 1th cubic segment and the ith cubic segment, and figure what that relation would look like. You'll have to bear with me here because the math is really quite involved. Let's continue. If you work out and simplify the math, you'll have the second derivative of the ith cubic segment written as 6 times 2t minus ti plus 1 over hi cube minus 6 times 2t minus ti plus 1 over hi cube, 2 times 3t minus ti minus 2ti plus 1 over hi squared, and 2 times 3t minus 2ti minus ti plus 1 over hi squared. This is your 1 by 4 row matrix multiplying this column vector here. yi plus 1, si, and si plus 1. Remember, the second derivatives of the I minus 1th segment and the ith segment at the common knot ti are equal. All you need to do is set I equals I minus 1 to get this expression. The composition of each term will be similar, just that ti is going to be replaced by ti minus 1 and ti plus 1 will be replaced by ti. Hi gets replaced by hi minus 1, yi gets replaced by yi minus 1, si gets replaced by si minus 1, and so on. On comparison, that is, when you impose C2 continuity conditions, we'll have this expression: 6 over hi minus 1 squared minus 6 over hi minus 1 squared, 2 over hi minus 1, 4 over hi minus 1 times yi minus 1, yi, si minus 1, si is equal to minus 6 over hi squared, 6 over hi squared, minus 4 over hi, minus 2 over hi times yi plus 1, si plus 1. Look how that complex math turns simpler as we go on. We can further simplify this and have this relation: si minus 1 over hi minus 1 plus 2 times si within parenthesis 1 over hi minus 1 plus 1 over hi plus si plus 1 over hi equals 3 times yi plus 1 over hi squared plus 3 times yi times within parenthesis 1 over h sub I minus 1 squared minus 1 over hi squared minus 3 times y I minus 1 over h I minus 1 squared. Now this is for I going from 1 to n minus 1. There's something important about this relation. Now, while we were doing the complex math that we just did, let's not try to forget what was the physics behind the entire discussion. Remember, I had mentioned that the slopes, in fact, at all junction points were unknown, implying that these slopes Si minus 1, Si, Si plus 1, they are all unknowns. What is known to us is the values at each junction point, Yi minus 1, Yi plus 1, and so on and so forth, and also the knots at each junction point. That is Ti minus 1, Ti, Ti plus 1, and so on and so forth. So here we have a relation that relates three consecutive slopes: Si minus 1, Si, and Si plus 1. Have you seen such an expression before? Yes. When we are discussing composite Ferguson curves, rather a C2 composite Ferguson curve. This condition right here is a condition for a generalized Ferguson curve. Going back, how many equations will we have here? I going from 1 to n minus 1. We'll have, therefore, n minus 1 such equations. How many unknowns will we have? We'll possibly have n plus 1 unknowns. Okay, let me copy the previous equation right here. And let me also observe a few more things about these equations. These equations are linear in the slopes Si minus 1, Si, and Si plus 1. The slopes which are unknowns are S0, S1 up till Sn. These are n plus 1 slopes or unknowns I had just mentioned a while ago. These equations right here are n minus 1 in number. We'll have, therefore, two free choices, or two more conditions that we would need to generate. Those conditions could be any one of the following. 1, free end, that is, no curvature at a knot. We call it a natural spline. Condition 2, built-in end. What do I mean by that? The first derivatives at the first knot or the last knot are specified as phi 0 prime t0, which is s of 0, or phi n minus 1 prime tn equals Sn. In other words, slope S0 and Sn are specified. Condition 3, quadratic end spans. Here, if the end spans are quadratic, the end curvatures are constant. So the two conditions that we need to solve the system of n minus 1 equations can be any two of these three conditions. Remember, for C2 composite Ferguson curves, we had specified the two end slopes as free choices. This is here a more general set of end conditions. Let's work with an example. Compute a cubic polynomial spline to fit the data points 0, 0, 1, 3, and 2, 0 with free end conditions. Let's assume the three knot values as t0 equals 0, t1 equals 1, and t2 equals 2. We have uniform norm spans here. H0, which is t1 minus t0, is 1, and H1, which is t2 minus t1, is again 1. I would want you to remember the mathematics that we had gone through. With that, we'll have the second derivative of the first spline segment evaluated at t0 as 6 times 2 times t0 minus t1 over h0 cube minus 6 times 2 times t0 minus t1 over h0 cube, 2 times 3 times t0 minus 2t1 over h0 squared, 2 times 3 times t0 minus 2 times t0 minus t1 over h0 squared. The column vector here will have entries y0, y1, s0, and s1. We know what y0 is, what y1 is, and s0 and s1 are unknowns at this time. We'll have an equation that will say 18 minus 4 times s0 minus 2 times s1 equals 0. For the second spline segment, phi1, we'll have a very similar expression. Phi1 double prime evaluated at t2 will give 6 times 2t2 minus t1 minus t2 over h1 cube minus 6 2t2 minus t1 minus t2 over h1 cube, 2 3t2 minus t1 minus 2t2 over h1 squared, 2 3t2 minus 2t1 minus t2 over h1 squared. The column here will have y1, y2, s1, and s2. Working on this equation gives us 18 plus 2s1 plus 4s2 equals 0. We have this equation in s0 and s1, and we have this equation in s1 and s2. For a moment, I was confused as to what I was doing. Okay. Now let's go back. We are saying that we are going to be using free end conditions. That would mean that the second derivatives at t0 equals 0 and t2 equals 2 will be 0. So the second derivative of phi 0 at t0 is 0. The second derivative of phi 1 at t2 is 0. So these are the two conditions corresponding to that. Now this condition is a familiar one. We have seen this before. Relates the slopes s0, s1, and s2. If you plug in the values of h0, h1, y2, y1, and y0, we'll have s0 plus 4 s1 plus s2 equals 0. So the three conditions will give us s0 equals 4.5, s1 equals 0, and s2 equals minus 4.5. If we compute what phi 0 t is, this is 1 t squared t cubed. We would be able to compute what the coefficient matrix is. You would need to compute the inverse of that, and we'll have y0, y1, s0, and s1 here. We solve or we simplify this expression to get phi 0 t as minus 3 over 2 t cubed plus 9 over 2 t. Likewise, phi 1 t will be 3 over 2 times t cubed minus 9 t squared plus 27 over 2 t minus 3. We now know what the analytical expressions of individual cubic segments phi 0 and phi 1 are. Let's plot them. The red curve here and the green curve here, they represent the first cubic segment and the second cubic segment. We get a shape very similar to a bell-shaped curve. But I'm not saying that these would correspond to our basis B-splines. We'll still have to do a lot of work to be able to get nice looking bell-shaped basis functions. In the lectures that will follow this one, we would like to design bell-shaped like basis functions, which will be composite polynomial splines, which will be locally barycentric as opposed to globally barycentric, which are the Bernstein polynomials. In a sense, we will be concentrating essentially on designing these basis functions.